Hi, I'm Mark Weitzman. Welcome back to our part 3 of the deep dive on the transformation of the W boson. And to briefly recap from last two parts, the problem is a fairly simple one. We have a coordinate system described by an observer O, and we have another observer O prime who's moving with velocity v in the z direction in O's frame, and we have a W boson which is a massive spin 1 particle. It's moving in the y direction. Its 4 momentum is given by, and I'm going to use Weinberg's convention throughout this the rest of this deep dive, where the fourth component is the time component. He did it in his chapter and I just followed him there. It's an old notation, but just think of 4 as being 0. So the momentum is given no momentum in the x direction, py in the y direction, no momentum in the z direction, and then the energy is given by the usual relativistic formula of the mass times the gamma factor. I'm going to put a subscript on that to indicate that it corresponds to this 4 momentum p, because we're going to have several gammas in this problem. And its spin component is given by sigma z equals sigma. And our goal is to find out basically what the 4 momentum is in O prime's frame. That's trivial from relativity. But then to find out what the spin component is in O prime's frame, and that's not so trivial. And last time we arrived at the following formula. The rotation, let me back up a second. What's involved here are 2 boosts, one in this direction and one in this direction. And what I showed last time, or at least I indicated, is in relativity, when you have 2 boosts in different directions, it ends up being factorizing as a single boost times the rotation. We showed last time that the boosts don't affect the spin component, but the rotation does. So we need to calculate this rotation in this angle. And this ends up being given by a fairly complicated formula. B indicates boosts. I have the inverse boost given by a velocity given by the boost of minus Vz applied to the 3 momentum from here. And I'll convert this for velocity, but then I think I'm going to go to a different convention anyway. And then here the gamma BP is the boosted, the gamma that corresponds to the boosted velocity, this thing over here. I called it gamma prime last time, but I'm going to go to a different convention, which I'll discuss in a second. Then we have the boost of minus Vz. Then we have a boost of Py over m gamma p. And because this is the velocity in the y direction for this particle, this is the gamma. So our kinematics I'm going to define our notation as follows. First of all, we're going to need gamma v corresponding to the boost from O to O prime. That's equal to our standard formula from special relativity. We won't use it, but 1 over the square root of 1 minus v squared. Our 3 momentum from here for p is just given by 0, py, 0. And the gamma p that corresponds to it, you would calculate it just using the standard Einstein relation, e squared plus m squared over m. This is just e squared equal p squared plus m squared. Now, I'll calculate it in a little while, but when we boost the particle momentum by minus Vz, we would get another vector, and I'll show this in a little while. For now you can accept it on faith. Minus gamma v m v gamma p. Now, what's interesting, and something that I won't prove to you here, but it's easy to verify, it's just a couple of lines of algebra, is that the gamma that corresponds to this velocity here is equal, and I'm going to indicate that by the notation gamma bp, is equal to gamma v times gamma p. It's one of the few simplifications in this problem, but this can be shown. You can do the algebra and work it out. Now, I've been using shorthand notation for these boosts. In actuality, in general, a boost has three parameters. We can either write it in terms of its velocity parameter, or I think what I'm going to do is I'm going to write it in terms of its momentum components. The formula is very similar. So this is just in general. If we're going to do a boost with these with a particle moving with this velocity or has this momentum, then I'm going to get this matrix, which has a lot of symmetries in it, so it's not that bad, but still you have to write it out. And again, I'm using the Weinberg convention that he uses in chapter 2, that he says he's not going to use in the book, but he does, of using the fourth component as time. This goes against the more modern convention of using time as the zero component. And so this general boost matrix, which some of you may have seen and some of you may not have seen, you can find it in Jackson. If you have the second edition, I don't know where it is in the third edition, it's at page 541. You can find it in Weinberg, volume 1. The equation number is 2.5.24. And so I'm just going to write it out. And the time components are very easy. And remember, the gammas here all correspond to these p's. So you would use like this general formula here. And then it's always a danger in doing this because now I haven't left myself enough room to write out the x, y, and z components. So this matrix, the whole thing is symmetric basically. So I'm just going to write it down as 1 plus gamma minus 1 px squared over p squared. Again, p squared is not the relativity momentum squared. It's just a regular px squared plus py squared plus pz squared. I have gamma minus 1 py px over p squared. Gamma minus 1 pz px over p squared. If you've never seen this, you should pick up a relativity book and get it. I'm not going to write down this is the same as that. Like I said, this matrix is symmetric, and the diagonal components, instead of px squared, I'll have py squared here, and I'll have pz squared there. Okay, so that's our general boost, 3-parameter boost for a Lorentz transformation. So let's start writing out what each of these boosts are. First one we have is B. I'm going to write them out in terms of momentum, not velocity. I'm going to be using this form because I wrote this with momentum instead of velocity. There's not much change at all. So we have 0, comma, the momentum would be, if this is a velocity, we would multiply by m gamma. So just 0 p py 0. And you should recognize this very easily from special relativity. So this really just comes from our usual equations, Lorentz transformations. Py over m is going to be like gamma v. So you might recognize this more in terms of gamma and gamma v, but I'm using momentum. Okay. Now our next boost is b 0, 0, minus v. This is equal to, again, this is easily recognizable. The only difference is, like here it's the y components, so you're going to have t and y's are non-zero. And here it's a z component, so you're going to have t and z's are not zero. Remember, you got to use the gamma appropriate to the velocity in the transformation. Here it's gamma v, here it's gamma p. Finally, our nasty looking one. I just want to, if we were to multiply this by the 4 vector, 0, py, 0, m gamma p, that would be equal to 0, py, minus mv gamma p, m gamma v gamma p. So that's what I said over here for the components. Remember, the 4th component is a time, so 0, py, minus mv gamma v gamma p. So we verified that, and then corresponding to this you calculate gamma bp, and you show that it's equal to gamma v times gamma p. It's a little algebra, not much. Okay, so now I have what I want to calculate is b inverse of this. If I multiply by, if I use the momentum instead of velocity components, I just would get rid of this denominator, and it's just the boost applied to the 3 vectors, so it's this over here. So that would be 0, comma, py, comma, minus mv, gamma v, gamma p. And the inverse of a boost, you just change the signs on the velocity transformations. So that's just equal to the boost of 0 minus py, mv, gamma v, gamma p. Okay. So to get this, you use this general formula, substitute for the py this, and substitute for the pz this. It gets messy, and I did it by hand, and I did it by software, and I checked that they're the same. I'm just going to write out the answer here. You can check it if you want. I don't think there's any way to avoid this messiness. And now I just gotta see if I can get enough room here, because I don't have that symmetry that I had in the other one. So it's gamma p times gamma v plus gamma p divided by 1 plus gamma p gamma v. Again, the gamma that you would use in here is gamma bp, which I'm using gamma v and gamma p, this product formula. That's why you won't see gamma bp in here, you'll always see these gamma p's times gamma v's. This is minus py over m, v, gamma v, gamma p, divided by 1 plus gamma v gamma p. This is minus py over m times v gamma p divided by 1 plus gamma v gamma p. This is the messy one, where we're losing our symmetry here. Gamma p squared, gamma v squared, divided by probably the same thing, 1 plus gamma v gamma p. These are time components are easy. Okay, so that's it. It's kind of ugly, and it gets even uglier because what we need to do is we need to multiply this matrix by this matrix by this matrix. So, as I said, I actually did this by hand and by software, and I may put my notes below this video showing the calculations. But once we do that, we'll get a matrix, and what we want to verify is it's a rotation matrix, and from that matrix we want to get the angle theta. Once we have the angle theta and the axis of rotation, once we have this whole matrix, we can figure out how to transform the spin components, and we'll start doing that in the next couple of parts. So I'll see you in part 4 in next time. Thank you very much.